have. We're treating Math 209. Alright, and today we are looking at numerical differentiation. We said the process of computing any value of the y dx for some particular value of x from a given data when the actual form of the function is not known is called numerical differentiation. Numerical differentiation. Alright, so quickly, without wasting much of our time, we will be tackling some questions very speedily. Alright, question number 1, example. It says from the table. Alright, so we said from the table below, compute the y dx and the squared y over dx squared for x equals to 1. And so because of this, we are going to be approaching the differentiation of these. Remember, our topic is numerical differentiation. So first of all, step 1, let's do it in steps. Step 1, we want to find out the difference table. We want to derive the difference table. Derive the difference table. So when you derive that, you have x, you have y, you have the change in x, you have the change squared of y, you have the change cube, 4 difference cubed, and you have the 4 difference to the power of 4 of y. Is that okay? Alright, now let's put that into perspective. Let's put 1, 2, 3, 4, 5, and 6. And then for the y's, we have 1, 8, 27, 64, 125, and 216. So what is going to be the change in y? Alright, what's going to be the change in y? So 8 minus 1 is 7. 27 minus 8 is 19. 64 minus 27, 37. 61 and 91. Remember, we are doing this minus this minus this. So the front minus the back. Is that okay? 8 minus 1, 7. 27 minus 8, 19. 64 minus 27, 37, like that, and so on and so forth. And so for this place, we have 19 minus 7. Is that okay? We have 12. 37 minus 19, we have 18. We have 24. We have 30. Is that okay? And then for the change to the power of 3, we have 6. We have 6. We have 6. And this minus this is 0. This minus this is 0. You have been able to derive the difference table. And so what do we do from here? This is our step 1. We derive the difference table. So this is how the question is going to come. You are going to see something like from the table of the value below, compute the y over the x. Mind you, this is an exam question. All right, this is an exam question. So let's quickly do that. So we said we have step 2. We're writing the parameters. Step 2 says write out the parameters. And so we have x naught is equal to 1. We have h is equal to 1. We have x is equal to 1. Since we are dealing with the beginning, right? X is equal to 1. You see that? For x is equal to 1. So we're dealing with the beginning. It says, which is at the beginning. Let me put that there. Is at the beginning of the table. So we use Newton forward formula. Newton forward interpolation formula. So remember, when we're talking about interpolation, right? When we're talking about interpolation, we broke them down into two. We said we have Newton forward interpolation. We said we have Newton backward interpolation, right? So now we're trying to differentiate. So the Newton forward interpolation is used for interpolating figures near the beginning of a table. Near the beginning of a table, right? And the Newton backward interpolation used for interpolating figures near the ending of a table. Near the ending of a table. And so now if you want to, the new numerical differentiation is you differentiating the NFI and also differentiating the MBI as the case may arrive. Now if you look at the question, it says from the table below, compute the y over the x for x equals to 1. So because we are treating something that is near the beginning of the table, we're going to be differentiating the NFI. And so if you differentiate the NFI, the y over the x is equal to 1 over h change y naught minus 1 over 2 change squared y naught plus 1 over 3 change cubed of y naught minus 1 over 4 change 4 of y naught as we approach infinity. Don't forget the NFI formula. The Newton forward interpolation formula says that what? Y naught plus u change in y naught over 1 factorial plus u minus 1 change squared y naught over 2 factorial plus u minus 1 u minus 2 change cubed y naught over 3 factorial as we approach infinity, right? Good. So if we differentiate this particular function, if we differentiate this NFI, we are going to arrive at this. You arrive at this formula. You understand me? So that is just what we are trying to say. When you differentiate an NFI, you're going to have a numerical differentiation that is going to give you this. The y dx will be this. All right? This whole thing. All right? So now that, and why are we differentiating the NFI? We are differentiating the NFI because we are looking for values close to the beginning of the table, right? Because they said compute the y over the x. So that means differentiation is coming into place. That means what? Differentiation is coming into place. So let's continue. So if we differentiate NFI, this is what we are going to have. We differentiate the NFI. This is what we're going. NFI means Newton forward interpolation. Newton forward interpolation formula. That's why we call it NFI. Is that okay? All right. So when we do that, this is what we're going to have, and then we can now say that the y over the x, as x is equal to 1 is equal to, we have written the parameters. X naught is 1 from the table. What is x naught? From this table, please, x naught is 1, x1 is 2, x2 is 3, x4 is 4, x5 is 5, x6 is 6. Is that okay? But you see, f of x naught is 1, f of x1 is 8, f of x2 is 27. You know what I'm doing, right? Good. So that is exactly what we are saying here. So what we'll be doing here is 1 over, so what is your h now? What is your h? Your h is the interval of differencing. In Maths 209, h means interval of differencing. What are the differences between the x values? You have 1, 2, 3. What is 3 minus 2? 3 minus 2 is 1. What is 2 minus 1 is 1. What is 4 minus 3 is 1. So the interval of differencing is the differences between the x values, which is 1. Look at it here, 1. So what is forward difference of y naught? From our difference table, we are going to be picking the first values. Since we are doing Newton forward interpolation, the first values. So the forward difference of y naught happens to be 7 minus 1 over 2. What's the forward difference squared of? That's 12, right? I believe it's 12. So we're going to put 12 here. Now plus 1 over 3. What's the forward difference cubed? We are here right now. What's the forward difference cubed of that? Forward difference cubed is 6. Is 6. You see that? So minus 1 over 4 into bracket 0 as we approach infinity. So the y over the x is equal to 7 minus 2 here 1, 2 here 3. That's 3, right? Okay, no, 6. 2 in 12 is 6, sorry. Mistake, my bad. 6 and we have plus 2 because 2 here 1, 3 here 1, 3 here 2. This is 0. This is totally 0, right? It's completely 0. So 3 here 1, 3 here, that's 2 plus 2. So our answer is 3. It means that the y over the x is 3. Now, because the question says not just solve for the y over the x, the question says you should solve for the squared y over the x squared. Solve the squared y over the x squared. And so if you want to solve the squared y over the x squared, what I'm going to be doing, you are going to be redifferentiating. You see that? We're going to be what? Redifferentiating the y over the x. That means you're going to be redifferentiating this person. You see? So when you differentiate that formula, what you're going to be having is, so you're saying the squared y over the x squared is equal to 1 over h squared into bracket change squared y naught minus y naught plus 11 over 12 change 4 y naught plus as we approach infinity. You might want to write these formulas down. You might want to write them down in case you see questions like this. All right, so now let's plug in the values. We have squared y over the x squared is equal to 1 over 1 squared into the bracket of 12. We all know that the change squared of y naught is 12. Is that not? From our table, the change square y naught, I told you we are picking the first value, the first values. So change square y is 12. So that's why we have it as 12, right? Minus, what is change cubed? That's 6 plus 11 over 12 of 0, right? As we approach infinity. So it means that the squared y over the x squared is 12 minus 5. Our answer is 6. Our answer is 6. So these are one of the very interesting things that we can learn about numerical differentiation. Now let's look at another example quickly. Let's look at another very interesting example. Example 2. Let's look at example 2. It says a rod is rotating. All right, so let's look at the question. Very interesting question. It says a rod is rotating in a plane about one of its end, right? And it says if the following table gives the angle radian through which the rod is turned from different values of time t seconds. It says find its angular velocity at t equals 0.7. So I believe 0.7 is around this region. And so because 0.7 is around this region, what we are going to be doing is what? Newton backward. If you look at the first question, at this question we have a Newton forward. Why? Because we're treating for x is equal to 1. So now we are differentiating Newton backward. Did you see that? We are differentiating Newton backward. You see? Find the angular velocity. All right? Find the angular velocity at t. So what do we do? Our step 1 is to do what? Is to try to derive. We derive the what? The difference table. That's what we do first. We derive the what? Difference table. So how do we derive that quickly? So we have t, we have 0 0.0, 0 0.2, 0 0.4, 0 0.6, 0 0.8, 1.0. We have pi, we have 0 0.0, we have 0 0.12, we have 0 0.48, we have 1.10, we have 2.0, and we have 3.20. So I'm just simply replacing what is in this table, putting them back into this. All right, so the next one I want to do is say a backward difference. That is the backward difference. So this particular symbol is the forward difference. It means forward difference symbol. This particular symbol is the backward difference symbol, please. All right, so because we're doing backward difference operator, so we are saying this backward difference of this will be this minus this. Just the same way you created the forward difference table. We have 0 0.12, then this minus this, we have 0.36. We have this minus this, we have 0.62. Let me just fill the table. We have 0.90, we have 1.20. Now we come to the backward difference squared of theta. We have this minus this, we have 0.24, we have 0.26, we have 0.28, we have 0.30, and backward difference cubed of theta. We have 0.02, we have 0.02, we have 0.02, and backward difference to the power of 4 of theta. We have 0 and 0. So we have been able to derive the backward difference table of that function. We have been able to derive the what? The backward difference table of that function. So what is the next thing? What is the next thing to do? What is the next thing to do? So we know that xn is equal to t of n. No, so the t of n we are looking for is the last man standing here. So in backward difference table, unlike the forward difference, Newton forward, we always say x naught. That's the beginning of the table, the first value there, right? Which is 0.00, 0.0. For this case is 0.0. But now we are doing the backward difference, Newton backward. So we're not going to be targeting the first value. You'll be targeting the last value on that table, which is what? 1.0. 1.0. So t of n, that n means ending. Let's just put it that way. It means ending. So 1.0. Is that okay? H is the interval of differences. What is the differences between these x values, these values here? What is the difference between 0.2 minus 0.0? Our answer is 0.2. Are we? What's the difference between 0.4 minus 0.2? Our answer is 0.2. That is, and so on and so. So H is 0.2. Is that okay? Now x is equal to t, which is what we are looking for, which is the one of 0.7, because from the question says find the angular velocity at t equals to 0.7 seconds. Is that okay? And so we have it that u is equal to x minus xn over 0.2. X minus xn over 0.2, 0.7 minus 1.0 divided by 0.2. Our answer there is minus 1.5. Our answer there is minus 1.5. And so let's not forget, don't forget that the Newton backward interpolation states that, this is the formula, states that if you are finding f of x, it will be equal to yn plus u backward difference of yn over 1 factorial plus u plus 1 backward difference squared of yn over 2 factorial plus u plus 1 u plus 2 backward difference cubed of yn over 3 factorial as we approach infinity. And so if we differentiate this function, if you find the dy over dx of this function, differentiate this function, you will be having something like 1 over h backward difference yn plus 2u plus 1 over 2 backward difference squared of yn plus 3u squared plus 6u plus 2 over 6 backward difference cubed of yn. This is the formula you are going to have if you differentiate this whole function. If you differentiate this whole thing here, you are going to arrive at this. So that's why I said if you write it down in your paper, in case you see this kind of question in the exam hall, you'll be able to use this formula just directly. You don't have to derive it. Is that okay? Now, if we are done with the derivation, then let's substitute. So we are saying that in this case now we're not using yn, we're using theta, we're using theta n, right? Okay. So our differential will be 1 over h into the bracket of this plus 2u plus 1 over 2 backward difference squared of this plus 3u squared plus 6u plus 2 over 6 backward difference cubed of this. Did you see that? So that is that about that. As we approach infinity, as we approach infinity, so it means that the theta dt, we are doing the theta dt now because of our table, the theta dt. Before it used to be dy dx, but now we're looking for angular velocity. That's why we're saying the theta dt. In the former example, you can see I said, in the former example, you can see I said dy dx. Look at it here. Here, the y dx. You can see that, the y dx. So it's not the same in this place because our table, what we did was theta and what we did was t. So it becomes the theta dt. It becomes what? The theta dt. So we have 1 over, what is our h, please? We have written our parameters, haven't we? Our h is 0.2. Did you see? Our h is what? 0.2. So we have it as 0.2 into the bracket of, okay, so 0.2 into the bracket of, we're following the formula. What is this guy? Backward difference of theta n. What is backward difference of theta? So in a backward difference table, you are picking the end. You are picking this, this, and this. In a backward difference table, you are picking the ending of the table. In a forward difference table, you are picking the first value on the table. But in a backward difference, you are picking the ending, the beneath. Okay, so this is 1 over 2 into bracket. What is the change square of this? That I believe you know that that's 0.3 minus. So if you that's no, sorry, that's not 0.3, that's 1.2. Let's check the table quickly. That's 1.2. Look at it here. 1.2. Please look at it here. 1.20. Sorry, 1.20. All right, 1.20 minus, if you do the calculation here, you're going to have minus 0.30 minus 0.0008. That's if you do the breakdown of from here to here. If you do the breakdown, this is what you're going to arrive at this. You're going to arrive at this. So the theta, the t is 4.496 radian per seconds. 4.496 radian per seconds. All right, so now the next thing we want to do is to find the squared theta over the squared the t squared, second order. We are redifferentiating. So at this point, you are what? You are redifferentiating the first, you are redifferentiating the theta dt. That's the first differential. The first differential that you did, which is this person here, you are differentiating this particular person. So if you differentiate that person, you have the squared, the theta over the t squared should be equal to 1 over h squared into the bracket this plus u plus 1 cubed of n, the theta n. All right, yes, plus 6u squared plus 18u plus 11 over 12 backward difference to the power of 4. All right, so the squared theta over the t squared. So this is what it's going to be. And then let's insert the values. We have it as 1 over 0.2 all squared into bracket 0.30 minus 0.5 into bracket 0.02 plus 0. If you follow it up with our table, the squared theta n is this person here, right? The cubed is this, the 4 is this. So if you follow that alignment, if you follow it up, you're going to have this. And then our final answer will be 7.25 radian per second squared. Did you see that? 7.25 radian per second squared. That's a beautiful one. That's a beautiful one. We have come to an end of numerical differentiation.